In today's video, I'm going to talk about valence shell electron pair repulsion theory, which is often called Vsepr. And so this is going to be a long video because we're going to go through all the different geometries, so feel free to watch it in chunks. So to start, let's talk about what Vsepr actually is. So it's a theory that's based on the simple idea that electron groups repel one another through Coulombic forces. So if you remember, Coulombic forces just tell us that opposites are repelled and opposites attract and like charges are repelled. So if all electrons have negative charges, then they aren't going to want to be close together in space. All right, so this brings us to the question of what are electron groups. Electron groups are lone pairs, or single bonds, multiple bonds, or even single electrons if we have the case of a free radical. So anything off of the atom is an electron group. So whether it's a lone pair or a single electron or a bond of any sort. So it could be a single bond, a double bond, or a triple bond. Those are all one electron group. Okay, so let's first start with CO2. So if we draw CO2, let me get my pen out here. All right, we have carbon in the middle, and we have oxygen double bonded on either side, and each oxygen has 2 lone pairs. Carbon has 8 electrons just in bonds, so it has no lone pairs. All right, so when we talk about Vsepr, we're going to be mostly looking at what is the geometry of the central atom. And so the lone pairs on the atoms that are not in the middle don't matter to us for this particular purpose. Okay, so for how many electron groups CO2 has, the carbon has 2 oxygens bonded to it, each through a double bond, but that doesn't matter. A bond is a bond. So it has 2 electron groups. I just said that there are no non-bonding ones, so we don't have to worry about that. So for bonding groups, we have 2. For lone pairs, carbon doesn't have any, so that's going to be 0. So the electron domain geometry is going to be linear because we have 2 electron groups. And in this case, since there are no lone pairs, the molecular geometry is also going to be linear. There are going to be some cases where the electron geometry and the molecular geometry are different, but if there are no lone pairs, then they're going to be the same. Okay, the easiest or the best way to get 2 molecular or 2 electron groups as far apart as possible to reduce repulsion is to have them be in a line, and so the bond angle is going to be 180 degrees. Okay, in this case, CO is a polar bond, but the polarity is going to go this way for this one and this way for this one, and they're going to be equal and in completely opposite directions. So the polarity for this molecule is going to be non-polar. Right, now let's draw a sketch of BF3. So we have boron in the middle, and we have 3 fluorines coming off of it. All right, and all of our fluorines have non-bonding pairs. But remember, boron is an exception to the octet rule. It doesn't have enough electrons to get a full octet. So we're done. We've used up all of our electrons now. All right, for electron groups, this has 3 single bonds and no lone pairs. So our electron groups total is going to be 3. Our bonding groups is going to be 3. And our lone pairs for boron, which is right in the middle, is going to be 0. Okay, the molecular geometry for this is called trigonal planar. And that's the same thing as the electron domain geometry because we have no lone pairs. The bond angle, the most effective way to get these 3 groups as far apart as possible is having them to be 120 degrees each. All right, so that's our bond angle, and they're all the same. And for these, again, boron fluorine bonds are polar, and they go this direction. But because these are all in the same direction, pulling in opposite ways, this ends up being a non-polar molecule. Okay, so now let's do CH4. So up here, I'm going to sketch how we usually write the Lewis structure. Okay, so we have carbon with 4 hydrogens bonded to it. So that's 4 electron groups. We have 4 bonding groups and no lone pairs. All right, our electron domain geometry is going to be tetrahedral. And if you remember from honors chemistry, I hope, the way we draw this is using the wedges and dashes. All right, so just a regular old line like I just drew in these last two indicates that that's in the plane of the board, or in the plane of the iPad in this case, okay? The wedge means that that hydrogen is sticking out toward you, and the dash means it's sticking back into the page. Okay, so this can't be drawn flat. It's not a flat molecule like the ones we've done so far. All right, so this, like I said, this geometry is called tetrahedral. And since we have no lone pairs, that's both the electron domain geometry and the molecular geometry. The angle here is the same for all of the hydrogens, and the angle is 109.5. I realize that's a weird number, but it is one that you need to remember because it's going to come up again and again. Carbon-hydrogen bonds are nonpolar, but even if this was like a carbon-fluorine bond, if they're all the same, they're pulling in equal and opposite directions, so the polarity is going to be nonpolar as long as all four of those things are the same. Now let's work on ammonia. Ammonia is NH3, so we have N, 3 H's, and we have 2 non-bonded electrons there on the nitrogen. So electron groups, we have 3 bonds and we have 1 lone pair. So altogether that makes 4 electron groups. And like I said, we have 1 lone pair, and then the 3 bonds makes 3 bonding groups. The electron domain geometry, since we have 4 electron groups, the electron domain geometry is going to be tetrahedral again. But if we draw out our molecule, the hydrogens with our tetrahedral geometry, and then the lone pair up there. We can't actually see the lone pair when we go to look at the geometry of the molecule, and so we don't want to include that in the geometry for the molecule. So though the electron domain geometry is still tetrahedral, since that one group is basically invisible to us, the molecular geometry is going to be trigonal pyramidal. The bond angle is still 109.5, okay, and in this case the polarity, each of the NH bonds is polar, and they're all pulling sort of up in this direction for each of them, and so that's going to make this a polar molecule. All right, now let's do water. So in water, oxygen's in the middle, and we have 2 hydrogens, and then the oxygen has 2 lone pairs, like that. All right, now a lot of times students think this looks linear when you draw it this way, which is usually how we draw the Lewis structure, but let's take a look at this in terms of the Vsepr theory. All right, so in terms of electron groups, we have 2 bonding groups because we have 2 bonds, and we have 2 lone pairs, so altogether that makes 4 electron groups. Anything with 4 electron groups, the electron domain geometry is tetrahedral. So if we go ahead and draw this, we have oxygen in the middle, we have 1 hydrogen over here, 1 hydrogen here, and then we would have lone pairs on either side, which again are invisible. So this angle here between the 2 hydrogens is still going to be about 109.5, all right? And then the other 2 things we can't really see. So the electron domain geometry is tetrahedral, but the molecular geometry for water is actually bent, and the bond angle is going to be slightly less than 109.5 because if you remember from honors, we talked about how the lone pairs actually take up a little more space because they don't have anything pulling the electrons away from that central atom. And so they'll push the hydrogens slightly closer to each other as a result of that. So the bond angle will be slightly less than 109.5. And the polarity of this, so the oxygen is pulling the electrons up this way in both cases. So this is definitely a polar molecule. Okay. Now let's move on to some of these are ones that have exceptions to the octet rule. So PCl5, phosphorus is here in the middle, and each of the chlorines comes off the central atom. Okay, and then all of those chlorines have non-bonded pairs. I'm not going to bother to draw them. So this is an exception to the octet rule. Phosphorus comes in with 5 valence electrons, so it shares each of them to make 5 bonds. So for the number of electron groups, this has 5, and they're all bonding groups, so 5 bonding groups and no lone pairs. And the geometry for this is called trigonal bipyramidal. Okay, so what this is going to look like is the phosphorus is in the middle, like I said, and then straight up and down from the phosphorus are 2 chlorines that are 180 degrees apart, and then one that's 90 degrees from each of those. Okay, and then this one is going to make a triangle with the other 2 chlorines. Okay, so each of the ones in this triangle here in the middle are 90 degrees from the other ones. So for this, there are 2 different bond angles. The bond angle between the chlorines in the triangle is 120, whereas the ones between the top and bottom and the ones in the triangle is just 90. Okay, in this case, the bonds are in equal and opposite directions, and so even if they were polar bonds, we're still going to get a nonpolar molecule because all of them are the same in different directions. So the polarity is nonpolar. All right, sulfur with 4 fluorines, you get the 4 fluorines that come off, right? And then there's actually a lone pair on the sulfur. There's also lone pairs on all the fluorines, but since we're just worried about the central atom, I'm not going to draw those. Okay, so for electron groups, we have 5 again. We have 4 that are bonds and just 1 that's a lone pair. The electron domain geometry for this one is, again, the trigonal bipyramidal. And what you'll see is that if we draw that as we did above, right, we're going to end up with the fluorines in this position and the lone pair out here. The reason the lone pair is out here is because that minimizes the repulsion. So it, if it was above or below, which would be the other possible position, then it's going to be 90 degrees from all the other fluorines. So this makes it, gives that lone pair a little extra space because, like I said, it has more repulsion than electrons that are in a bond. And so this molecular geometry is called seesaw. So you can kind of see over here would be the fulcrum of the seesaw, and then this part would be the part that goes up and down if you turn it sideways. All right, the bond angles here, it's going to be 180 for this fluorine-fluorine bond, 90 for that bond here, and then for this bond here is going to be 120. So there are 3 different bond angles for this particular geometry. And the polarity for this one is going to be polar because we have definitely an uneven symmetry here because this whole side over here doesn't really have any bonds sticking out. So it's definitely asymmetrical. So it's polar. For BrF3, Br is going to go in the middle. And then we have the 3 fluorines around. And the bromine here in the middle has 2 lone pairs on it. So for electron groups, we have 2 lone pairs, thus the 3 bonds makes 5 electron groups. And I just said there's 3 bonding and 2 lone pairs. The electron domain geometry, when you have 5 electron groups, is always trigonal bipyramidal. And then for this case, we are gonna keep those lone pairs right where I've drawn them. They'll still be in the equatorial position, so that triangle that's there in the middle. And our angles are going to be 180 degrees and 90 degrees. All right, and then because this is asymmetric, just like the last one we looked at, it's going to be a polar molecule. For xenon difluoride, we have xenon in the middle. We'll have our 2 fluorines here, and then the xenon has 3 lone pairs on it. Okay, so we have 3 lone pairs, 2 bonding groups, so that makes 5 electron groups altogether. So again, the electron domain geometry is going to be trigonal bipyramidal. And the molecular geometry in this case, since we can't see any of these lone pairs, is just going to be linear. Okay, and so the bond angle is going to be 180 degrees. Since the 2 fluorines are the same in this case, and they're pulling in opposite directions, the polarity of this one is nonpolar. All right, now let's do SF6. So we have sulfur here, a fluorine up here, fluorine down here. Okay, and there are no lone pairs, so this is, well, there are lone pairs on the fluorines, but there's no lone pairs on the sulfurs, which is what we're concerned about. So that's 6 different groups, so 6 electron groups, they're all bonding groups, no lone pairs. The electron domain geometry for something that has 6 electron groups is called octahedral, okay? And what it looks like is very similar to what I just drew, but you have the fluorines coming above and below, and then the other 4 make a square in the plane. So one's going back, one's going this way, and this way. And just a side note, if you're having trouble visualizing these from my drawings, that's understandable because my drawings aren't very good. We're going to spend some time on these looking at models in class, so don't freak out yet if you don't understand them. There are also pictures in the book that might help you, and we're going to use a simulation that will help you move them around in 3 dimensions and hopefully get a sense of what they look like. All right, so since we have no lone pairs, the molecular geometry is the same, again, octahedral, and all of the angles in this, this geometry are 90 degrees. Okay, everything here is the same, pulling away from the sulfur, and so the polarity, since it's completely symmetric, the polarity is nonpolar. All right, now let's do BrF5, so put Br in the middle, fluorine. All right, and then we have 2 non-bonded electrons there on the bromine. All right, so the number of electron groups here is 6. Again, 5 of them are bonding, 1 is a lone pair. The electron domain geometry for something with 6 electron groups is octahedral. The molecular geometry in this case, since one of the sites is sort of invisible because it's the lone pair, we end up with a square pyramid. So let me draw this a different way so it's easier for you to see. So if we put the lone pair down there, then we again have our square that we make with this, and then one more up here. So if you were to connect all those fluorines, you'd get a square pyramid. So the molecular geometry is square pyramidal. The bond angle here, again, is going to be just a little less than 90 degrees. Anytime you have a lone pair, it's going to push the atoms a little bit closer to each other because that lone pair is so much negative charge. So slightly less than 90 degrees. And the polarity of this is going to be polar because everything is moving up toward that top fluorine, and you just have this lone pair down here on the bottom. All right, now the last one for this part is excuse me, XeF4. So we have xenon and we have 4 fluorines. All right, and then so the 4 fluorines form a square, and then the 2 lone pairs above and below would be above and below that square. So again, we have 6 electron groups. 4 of them are bonding in this case. 2 are lone pairs. The electron domain geometry is again going to be octahedral, but the molecular geometry here is square planar. Okay, the bond angles are going to be 90 degrees in this case because the 2 lone pairs are pushing equally from the top and the bottom, so it doesn't affect the bond angles. And the polarity here would be nonpolar again because those fluorines are all pulling out in equal and opposite directions. Now for these last 3 examples. I'm going to do the work and just put it up here, but I'd like you to pause the video right now, try to do it yourself, draw the Lewis structure, make fill in the rest of the table, and then restart the video and check your work. So I'll do that for this one and for the 2 on the next slide as well. So here are the answers to SCL2. Hopefully that's what you got, and if not, you can come see me and ask questions. And here are the answers for I3 minus and for PF3. So again, if this is not what you got, come see me and I can help you and we can go through the examples in more detail. And then the last one is IF4 plus. So here are the answers for that one. If you did not get them, again, come see me and I can help you out. And we're going to do more practice with these in class, so you'll get lots of practice trying to visualize these in 3 dimensions.